Welcome back to the course of crystallography. In the previous couple of lectures, we have discussed about handling the data with a couple of software. We have seen how a Bruker software or a Rigaku software can be used to analyze the recorded data, and then how one can solve structure and do refinement using OLEX2, and for that you use ShellX for structure solution and refinement. And then in the previous lecture we discussed about how to understand the intermolecular interactions, how to identify the intermolecular interactions using Mercury, how to get some basic molecular parameters, the interplanar angles and all that using Mercury. And also I have shown you how you can generate the simulated powder X-ray diffraction data using Mercury for comparison with the experimental data. So the data that is simulated from this single crystal data should then be merged or should then be compared with the observed experimental powder data on the bulk sample, and if all the peaks match 1 to 1, then you know that the bulk sample and the single crystal are one and the same. But it may so happen that during the crystallization process from different solvents, you might have resulted in a different crystalline form which is different from the original powder that was used to grow the single crystal. So in that case, the powder X-ray diffraction data simulated from the single crystal will not match with the observed powder pattern on the bulk sample, and the peak positions will be different, peak intensities will be different, and that will indicate that you have got a different crystal structure which is called a polymorph, and you characterize it as polymorph A, B, C or alpha, beta, gamma, whatever. Polymorphism is another phenomena which we should discuss in one of the classes. Just to brief you that a particular compound is potentially possible to be arranged in 3 dimensions in more than one different ways to grow a crystalline architecture. So a compound which can have a multiple number of crystal structures are called to have polymorphs, or we call them as polymorphs. That means many forms of a particular compound in crystal structure. Today we want to now discuss about the possibility of disorders in crystal structure. Disorder in crystal structure. What do we mean by disorder? Disorder means the atoms not being fixed at one place. The origin of this disorder could be of two types. One can be a dynamic disorder. The other one can be static disorder. In a dynamic disorder, the main reason for that is the thermal motion of the atoms or molecules. And static disorder means more than one location or orientation of an atom or a molecule or part of it. So this dynamic disorder, which is mostly due to a temperature effect, it may so happen that we have a perchlorate anion which is tetrahedral in geometry. At room temperature, the chlorine may have a very large thermal ellipsoid, which means the chlorine is vibrating in along x, y and z. As a result of that, the oxygen atoms which are connected also are vibrating in all the possible directions with respect to those oxygens as well. So what we get is overall a picture which has a very large ellipsoid for chlorine and very large flat type ellipsoids for oxygens, which actually form a tetrahedra, but that tetrahedra is highly distorted. One can treat this data by splitting all the atoms into parts. So what you do is you split all the atoms in two parts and refine with some constraints. So when you do that, for every splitted portion, you have one set of 5 atoms as I am trying to draw. See, I am drawing them slightly shifted because they are on a particular thermal motion. So now if I have the first set numbered as Cl1, O1, O2 and O3 and O4, the second part will be numbered as we can number it as Cl1A, O1A, O2A, O3A and O4A, and for the chlorine, again for part 2 we write it as 1B, O1B, O2B, O3B and O4B. These are the 4 oxygens of green molecule and those are the 5 for the red molecule. So what we have is, this is called the part 1 and this is called the part 2. We end that part 1 with a command part 0 in the INS file. You also end this as part 0, which means the disordered parts are over. Then what you have are the corresponding atomic coordinates x1, y1, z1 and all the atomic coordinates for all of them. Similarly for this you should have x1 prime, y1 prime, z1 prime and all of them will have their corresponding xyz coordinates after splitting, and then you will have a term for occupancy. As I said, the occupancy parameter is generally written as 11.00 for 100% occupancy, but in case of this disordered structure, instead of writing it as 11.0, we write it as the first part as 21.000, and we write all those as 21. And then for the second part, we write this as minus 21.000 for all of those. And in this instruction file, at the top, we will have one line written f var. So at that point, we identify to start with as 0.5. That means this 21 represents 50% occupancy, minus 21 represents 50% occupancy. When we try to refine the structure depending on the actual electron densities at those two sites, this quantity in F var will keep on changing. It may so happen that on doing several rounds of refinement, this F var parameter stabilizes down to like 0.7203, which means this is about 72%, and this is the remaining, which is about 18%. So this then refines the relative occupancies of two different orientations, or rather two different locations of those two groups, and then those two anions of perchlorate, and it refines down to a particular occupancy. And then at the end, as usual, you will have the isotropic thermal parameter for all of them, which also will be independent parameter and will be refined along with the refinement of occupancy. So once with isotropic refinement we have converged to the least square refinement convergence, then one should do anisotropic refinement and get that U iso to get converted to those 6 anisotropic thermal parameters. So this procedure is followed when there is a disorder, as I have discussed in case of perchlorate. Actually, this method of refinement, the way we talked about it, is part 1 and part 2. This is done in case of all kinds of disorder treatments using the Shell-X within OLEX2, or even if you are using with WinGX is another package. Now, if you see that the coordinates of CL1 and coordinate 1A and coordinates of CL1B are very, very similar, or they are exactly same, and also the corresponding thermal parameters for those are also very similar, you can then constrain or restrict that both chlorine 1A and 1B should have the same location and same thermal parameter. So to do that, one can use two commands simultaneously. The command is EXYZ, which means the two atoms that we are going to write have the same XYZ coordinates, that is equal XYZ coordinates. So we write it as EXYZ, and then we name those two atoms, suppose Cl1A and Cl1B, which means they will have same coordinates. Then another command we write as EADP, which means equal atomic displacement parameters, and you write Cl1A as Cl1B. What it would do is, it would place both Cl1 and Cl2, that is Cl1A and 1B at same place with same thermal parameter, and then have the other oxygens refined over a set of 4 coordinates, and the refinement would bring your R factor below 10%. So, this type of disorder that we can handle, and this can be reduced by doing it at low temperature, because on lowering the temperature the atomic vibration will reduce, so that the atoms that are present in this particular molecule will have a smaller thermal vibration, and as a result they will be more confined towards their nucleus and the disorder will be reduced. So, this is a dynamic process. On increasing the temperature, disorder increases; on decreasing the temperature, the disorder reduces, is called a dynamic disorder. The other type of disorder that one can have is, as I already indicated, is called static disorder. This also can happen with a perchlorate anion or any such anion. As we are discussing with perchlorate, let us stick to that. It may so happen that in the structure at some equivalent position, the perchlorate anion is oriented like this, and in another site the same perchlorate is oriented like this. Which means at some place the perchlorate is oriented like that, 3 oxygens pointing towards left, and in another side 3 oxygens orient like this, but the 2 oxygens which are here, they are at same crystallographic location. So, as a result, what will happen is that this group will actually be looking like that. And this 2 different orientation of the perchlorate is not a result of thermal motion. It is an intrinsic disorder that is present in the lattice. So, the perchlorate anion at different site is oriented in different way. This particular type of disorder cannot be lowered or reduced or removed by lowering the temperature. So, if you lower the temperature, what will maximum happen is the thermal motion of those individual oxygen and chlorine atoms will reduce, but still you will be able to see that in the asymmetric unit you have atoms which gives you a feeling that it is like this. So, it actually means that this middle oxygen is serving the common atom for both sides, and these 2 sides have different chemical occupancies. It may so happen that one side is again 60%, the other side is 40%. So, in that case, the same type of part 1, part 2 kind of refinement has to be done with appropriate identification of those atoms and numbering them appropriately, and then we apply the EADP and EXYZ constraints on the central oxygen, which is a part of two disordered portions. A similar type of disorder is also seen in many cases. Suppose if you have a molecule like this, the way I am drawing, it is a derivative of isoquinoline, and then you have a fluorine atom here. It is possible that this molecule has a free rotation about this CC bond, which is from C1 to this aromatic ring, and because of that free rotation, the fluorine on that can appear on either side. And it was seen in our lab as one example. This fluorine is on one side about 60%, and the bond is rotated exactly 180 degree, making the fluorine on the other side appearing for 40%. So 60 and 40, this disorder is not controlled by the cooling, because when the crystal has grown, the molecule has crystallized in such a way that the 60% of the molecules have the aromatic ring rotated in this orientation with fluorine towards the left, and 40% of the molecules have crystallized with fluorine on this side. And at room temperature in solid state, this orientation of phenyl ring is restricted. So this rotation is only allowed in solution. So from room temperature to low temperature, we cannot convert all of them to one direction. So what we can only do is we lower the temperature, we reduce the thermal vibration of all the atoms in a molecule, and then treat those individual atoms as two splitted portions. So here what will happen is we have 6 carbon atoms which should be splitted, but treated with both EADP and EXYZ commands, because on rotating one ring from this orientation to that orientation, the carbon atoms have fallen on the same place, not at different places. As a result, the coordinates of carbon atoms are same, but the fluorine is changing its orientation from this side to that side. So that orientation being different, the fluorines will not have corresponding EADP or EXYZ. They will have their own atomic coordinates, should be defined separately using the fvar command, that is the free variable command, and doing it in +21 and -21. In case in one particular crystal structure, if you have more than one group of atoms having different types of disorder, then the thermal parameters that you encounter, or the occupancy parameters that you encounter should have numbers continuous. So suppose if part 1 and 2 corresponds to a disorder of one perchlorate group, so that occupancy should be designated as +21.00 and -21.00. Then there may be part 3 and part 4 corresponding to another molecule of ClO4 minus, that should be designated as +31.0, -31.0, and so on. If you have large number of parts to be disordered, large number of anions or part of the cation itself or the part of the original molecule disordered, as many disordered sections you have, you should keep on going plus 31 minus 31 plus 41 minus 41 and so on, and refine them as independent portions which are disordered and are being treated separately. Of course, by doing all these, it may so happen that the number of refinable parameters may increase so much that your data may not support that refinement to happen efficiently, and as a result the R factor may get increased. It may so happen the refinements may not converge, and one has to then take a decision up to what point one should actually keep on doing this refinement. If we reach a limit beyond which we are not able to refine, we should stop and get back to our work and make points suitable for the comments that we can make at the structure refinement part while writing the publication, that this data cannot be further refined using more disordered fragments. At this point, I would like to mention one important aspect. These disorders that we are discussing are treatable disorders using SELEX, because these are intrinsic disorders which was incorporated either by temperature effect or by crystallization effect. But there are certain kind of disorders which we have encountered in many crystal structures, which is a random disorder. And that random disorder is a result of a thermal shock given to a crystal. Suppose you have a crystal kept at room temperature, but your diffractometer equipped with your cryosystem is running at 100 Kelvin temperature. You take the crystal from room temperature, mount it, and then directly mount it on the goniometer and put it on the diffractometer. In a fraction of a second, the crystal is cooled from room temperature to 100 K. This cooling in a fraction of a second results in a peculiar disorder of all the atoms, maybe all atoms or some of the atoms, which had very different thermal vibrations at a given temperature. So, because of this thermal shock, some molecules may be frozen in a particular orientation, some molecule may be frozen in a different orientation, some molecule may be frozen in a different orientation because of its very high thermal motion at room temperature, and the result is a highly disordered structure at 100 Kelvin. So, it becomes extremely difficult to treat that kind of disorder, and this is random. To avoid such a situation, we always recommend that you take a crystal at room temperature, slowly cool the crystal to 100 K so that you allow all the molecules to slowly reduce their temperature and refine their thermal vibrations, and then come to a thermal minima and then fix at one place at 100 K. Because at room temperature it is possible that different anions at different locations of the unit cell are vibrating in a different manner. As a result, they are not only vibrating, they may be slightly rotating also at room temperature. So, when you try to cool it very slowly, they always reach a state of equilibrium of lowest energy, and at 100 K you may see that the disorder has disappeared, which you might see at room temperature. But then if you suddenly cool a crystal from room temperature to 100 K in a fraction of a second, all those dancing, vibrating, jumping molecules or ions will be frozen at its sudden location, and the result will be seen in the asymmetric unit, which will have the anions or molecules or parts of molecule oriented in different ways with different types of occupancies, and it will become a very, very cumbersome situation to refine those in a given scenario. Even the data, if it is not a good quality data, it may not be possible to treat that disorder suitably to reach a lower R factor. That is why one has to really worry about the data collection procedure, one should be patient and collect the data with as much care as possible, because you may be collecting a data in 2 to 3 hours time, but if the data is not of good quality, then you may be spending several hours, 10, 15, 20 to 30 hours to do the structure solution and final refinements of a poor data. So in today's class, we have discussed about the treatment of disordered molecules, how to handle these disordered structures using the refinement software. In the next lecture, we will try to show you one such disordered structure treatment in reality.